Hello students, welcome back to another lecture on classical mechanics. Today we have the lecture number 18. In the last class we have discussed the details on the Poisson bracket and how the Poisson bracket is going to be very useful in determining the constants of the motion. We will see more details on the Poisson bracket and then the determination of the constant of motion that we will do in the continuation of this after this lecture. And today's lecture plan is that before entering into details on Poisson bracket itself, let us have more clarity on the calculation of the Hamiltonian, because we have been discussing the Legendre transformation for some time, and then the Legendre transformation is going to help to convert the given Lagrangian to the Hamiltonian. So that is the purpose of the Legendre transformation. And during the transformation, I also explained, or I also informed you, that the calculation of the Hessian matrix is very important, because in case if the determinant of the Hessian matrix is 0, then it is not possible to find the Hamiltonian. So that is a point that you'll have to remember. So since these points I already explained you, it is an appropriate time now to demonstrate two things. One is the calculation of the transformation itself. The second demonstration is that how Hamiltonian can represent the total energy of the system, because I did not tell anywhere that Hamiltonian is going to represent total energy, right? In terms of expression. Okay, maybe while explaining or while speaking, I would have told that Hamiltonian may represent total energy. But however, we have not performed any calculation and showed that Hamiltonian can represent total energy. Such a calculation we have not done. So today that is a plan now, and the calculations are going to be fairly simple, because you already know the standard definition for the Legendre transformation, what is meant by Hessian matrix, and these kind of things you already know, and therefore we can proceed further. So first of all, we will take the second one, because the first one involves Hamiltonian, right? So the moment Hamiltonian is entering into picture, let us first finish the Lagrangian to the Hamiltonian transformation. Once it is transformed, then we will come back to the part A, namely the how it is going to represent the total energy. So that is the plan now. Now what we will do is, in order to take this particular situation, we will consider an example scenario. So I'll write down here that provided that we have the Lagrangian with us, we can proceed further to see how the calculation is actually being performed. Okay, so for that purpose, we will consider an example where the Lagrangian for some two-dimensional system is given by this expression of m into r dot square plus you have r square theta dot square, then minus some constant times the r. So as you can see that we, even without expressing whether it is 2D problem or 3D problem, now you should be in a position to decide what kind of problem it is. Okay, most of the time they will not tell whether it is cylindrical coordinate or spherical system, etc. Most of the time you'll have to see the appearance of the equation and then determine whether the given problem belongs to the Cartesian or cylindrical or whatever it is. So that is the first thing. Second thing is whether the given problem is three-dimensional problem or 2 degrees of freedom system. So those things also you have to decide. So only the Lagrangian only will be given. The rest of the thing you'll have to find out. So here what you understand from here, so that is what is the idea now. So solution technique. So first of all, what is the aim here? Our aim is that given a Lagrangian, so this is the Lagrangian for a certain problem. What problem also we are not interested in. So some problem, some dynamical system, this is the Lagrangian that is given in your question paper, and our objective is that, our aim is that you'll have to find out, or that means you'll have to perform the Legendre transformation and then find out what is the Hamiltonian corresponding to this Lagrangian. Okay, corresponding to this Lagrangian is very important. So this is the objective of the question, and then we will proceed now further. In order to perform any calculation, first of all you need to understand what the Lagrangian is made of. That means, what is this Lagrangian a function of? Lagrangian is a function of, you just find out what are the variables. 1/2 constant. Mass is a constant. So constants you don't bring inside. K is a constant. It is given in the question paper that K is a positive constant. So that is given in the question paper, and therefore that is constant. We don't bring it. We need to be careful whether it is positive constant or negative constant, because this sign will change. Okay, so for that purpose, generally in the question paper they will give that it is a positive constant, which means this minus will not be disturbed. That's the point. So now the Lagrangian is therefore a function of what? So you know that Lagrangian is going to be a function of q comma q dot comma t. So this is the standard way of writing down, and since there is no time dependence in our equation, it is very clear that Lagrangian is going to be a function of q and q dot only. So that is clear. Now our aim is therefore we will have to write down all the variables. First we will write down the variables without dot, and next we will write down the corresponding dotted version. So you have to find out what are the quantities without dot. So you have an r here, therefore we can write down that it is a function of r, then comma, then whether theta is there, it is not there, but even then you see what is the meaning why I am writing theta. So there's a theta here. Why I am writing theta is because after that you will have to write down the dotted version. So what are the dotted versions? Are there r dot? So r dot is there here, and then comma, you have a theta dot here. So therefore theta dot. So in fact, now you can ask the question, why did I write this particular theta even though it is not there? Is that when you write, the important point that you'll have to remember is there should be as many number of dotted variables as there are undotted variables. Okay, that means if there is one q, there will be one q dot. If there are 20 q's are there, then there should be 20 number of q dots should be there. So even though they are not visible, or even though they are not explicitly present in the given Lagrangian, you can always write that it is a function of those variables. Okay, you can always have missing variable, that is fine, but the number should be matching. If there are two dotted variables here, you have r dot and theta dot, two of them are there. You should also have two number of undotted variable without dot. That is a requirement. Okay, so that is the most general way of writing down the appearance of the Lagrangian, and you can always say that in the given Lagrangian theta is missing. Okay, so that is always there, and then you can later find out, and you can write down that q happens to be, or rather than q, we will say that exactly theta, right? So in our problem, theta is the cyclic coordinate. So first of all, you will have to write down by making the count correctly. Okay, number of dotted variable and the number of undotted variable should be equal. So in that way you write down and then find out what are all missing there, and those missing quantities are known as the cyclic coordinate. Cyclic coordinate is also known as the ignorable coordinate. So that's all. So that is fine. This information you keep it aside. And now comes the question that once you write down the appearance of the Lagrangian like this, so what is your conclusion? That the conclusion means what can you say about the number of degrees of freedom? So I'll write down that number of degrees of freedom for the given problem is equal to how many number is there. You'll have to see whether you can either count the number of dotted variable or you count how many undotted variables are. It doesn't matter which one you are going to count, because here we have an equal number only we are going to maintain. So here we have two of them are there. So two variables are there, whether it is dotted one or undotted one, and therefore we will say that the given problem is a 2 degrees of freedom system. So this is your first claim that you can have. In case if you want to know about whether it is Cartesian system or spherical polar system, then generally we allow to see the appearance of the symbol and then decide. Since you have r and theta, it is going to be a two-dimensional plane polar system, because number of degrees of freedom 2 means certainly it cannot be 3D cylindrical or 3D spherical system, because degrees of freedom 2 means it should be two-dimensional one. In the case of the two-dimensional one, it is automatically plane polar coordinate system. So for the plane polar coordinate system, you know that r comma theta are the standard variables, and therefore you will be now in a position to agree that the dynamics is taking place in a plane, and the coordinate system used is the two-dimensional plane polar coordinate system. So these kind of information can be gathered if you can make and write down the information like this. So you got some idea about the given problem, and you have some kind of information on the number of degrees of freedom. So now the next step is that you'll have to now write down the defining equation for the generalized momentum, because our objective is that you'll have to calculate the Hamiltonian. Okay, for the Hamiltonian calculation, your first step is that you have to write down the defining equation for the generalized momentum. And the standard definition says like this: the partial derivative of the Lagrangian divided by dou qi dot. This is the general definition. This will be defined as, so I'll write down that this is the defining equation, and it says that this should be equal to the corresponding momentum. So the corresponding momentum is what we say conjugate. Okay, it is the conjugate momentum to the variable qi. So this is the standard definition, and now you'll have to see that what is the meaning of the suffix I here, where the I will take the values 1, 2, etc. up to n number of degrees of freedom, where this particular n is this particular n that we have written is the number of degrees of freedom. So therefore, now you understand that once this is clear, now you'll have to express clearly the defining equations. Okay, even though it looks like qi and pi, we don't have qi pi in our given problem. You see, our problem has r comma theta or dot comma theta dot. You don't have qi pi. So that is why generalized expressions should be now have to be written for specific expression. So for our problem, that means for a given problem, we will have to rewrite this particular definition with respect to our variables. Now, what is the number of degrees of freedom for our system is that we have 2, and therefore we have to clearly identify what is this qi here. So therefore I write down that qi will be, therefore it becomes q1 comma q2. Since 2 numbers are there, we have to write q1 comma q2. So what are those q1 comma q2? We clearly identify. The first one will be r, because these are the generalized coordinate, and therefore the second one will be the theta. So which means that your understanding is that q1, wherever q1 comes, in that place you'll have to put r, and wherever q2 comes, there you'll have to substitute theta. That is the meaning, that qi. So once this kind of symbols are clear for you, then it will be then you will feel more comfortable to solve a problem. And similarly, the corresponding pi also you'll have to write down correctly, that this has to be the what you call pi means the momentum, right? So you'll have to write down p. Here you have to be careful, p. Then we have to say this is p1, then comma, then we have a p2. Then what happens is, what is this 1 and what is this 2? That should be clear. So 1 means, see here, 1 means you have to write r, and therefore you'll have to write down this is pr. So this is the notation you'll have to use. Then comma, p2. What is 2 here? 2 means 2 corresponds to the theta variable, and therefore you'll have to write down this is p theta. So this is the symbol that we have to use in our problem. So this will be the symbols for pi. So this is very important, because in the defining equation, you see that there is a qi dot and then there is a pi dot. So therefore, pi. So we need to know these things clearly. And the corresponding dotted variables, that is not a problem. Dotted variable, you can always keep the dots, which means that I will now write down that qi dot. So qi dot means you can now write down that q1 dot, then you have a q2 dot, then comma. So what are they? So you have to see here, this is r comma theta, and therefore this must be in r dot comma a theta dot here. So this will be your qi dot. So now all the details are now clear, that what are the variables that you will have to use. That means, let me put a tick here. qi is the one that we need now. qi dot is the second thing that we are interested now. I'll put line here. So qi and qi dots are here, and therefore in this place we will have to use, and then in addition you have a pi here, and for the pi we have to use this symbol. So symbols should be clear. Once the symbols are clear, now we are ready to write down the defining equations. Okay, so for the given problem, so for our problem, for our problem, so what are the equations that we have is that partial derivative of the Lagrangian divided by dou q1 dot. So first of all, you'll have to write down dou q1 dot will be equal to p1. That has to be simplified, or that has to be rewritten like this: dou L divided by the first coordinate q1 is r. Therefore, we will say r dot. That will be given by PR. Okay, so you have to take care of this kind of symbols that I have explained. Only then it will be clear, and you feel comfortable that this equation is now clear. Dou L divided by dou R dot equal to this. Now evaluate. So from here, what you do is now evaluate this partial derivative. From where will you evaluate? From the given Lagrangian, because Lagrangian is already given. So you'll have to remember what is the Lagrangian or keep it with you separately. So this is the expression for the Lagrangian which is given. And from here you will have to evaluate the partial derivatives, and then we will substitute there. Okay, so keep this Lagrangian and then simplify the expression for the partial derivative. So that's what we are going to do now. So that gives you, so that means this is equal to, so the partial derivative of the Lagrangian with respect to the r dot is given by, there is a half here, then there was a m here, open bracket, then there was an r dot square, so I will be getting 2 times r dot, plus the next term is actually r square theta dot. So there is no dependence on r dot, and therefore that will be equal to 0. Then you have minus k times r. K times r, derivative is 0. Okay, so all the terms we are differentiating with reference to the, or with respect to the r dot. So this is what you get, and all that, if you simplify, you are supposed to say that that expression is given by PR. So write down that this is PR. So simplify this, we will be having m times r dot equal to PR. So this is the first expression that you can have. And then remember that this is now we are having the 2 degrees of freedom system, and therefore this job we have to do 2 times. Okay, so this is where you have to be, you are now getting experience in the sense that the number of degrees of freedom, if it is there, if you are going to have 6 degrees of freedom, this equations you have to write down 6 times for each one of the coordinates. Okay, that clarity will come when you are solving a problem. If you are writing a theory, then what happens is you simply say that I is equal to 1, 2, etc. up to n number of problems. Like this you write and then stop. But when you are solving a problem, now you can't write like I equal to 1, 2. Like that you can't write. You have to actually write down the corresponding equations. Okay, so therefore we will say that this is let us say that this is our equation 1 for 1 degree of freedom. Okay, now we have to work out for the another degree of freedom, that is the second degree of freedom. So that is what we are going to write, and corresponding to the second degree of freedom, we will have to again start with this particular defining equation. Therefore we will say that this is dou L divided by dou Q2 dot, because second 2 means second degree of freedom. So that will be given by P2. And now you'll have to simplify this. That means dou L divided by, what is our second variable? Theta is our second variable. Therefore, we'll write down that this is dou theta dot. That will be denoted by the symbol. Here there is nothing to do. You have to simply write down P2. But however, as I already told you, 2 means the second variable, and our symbol actually is theta, and therefore we will have to substitute P theta here. So that is the symbol that we will be having. So now what you do is you take the given expression for the Lagrangian and then differentiate with respect to the theta. So if you take that, what are you going to get? Let us see. Half into m into, our first term is actually r dot square, therefore its derivative is 0. Then plus you have r into theta dot square, right? So r into theta dot square means I will be getting here r is there, then you get theta dot square means 2 times theta dot I will get. Is it okay? So that's all. Then minus k times r. So for k times r means differentiation will give you 0. And all that thing, if you simplify, this expression is the p theta. And that's all about it. And then simplify this, we will be getting 2 is getting cancelled. We will be getting m into r into theta dot that will be equal to p theta. So this is your second equation. So our first step is now completed, which means that we have our first step is completed means what do you mean say? Our defining equation, that means our generalized momentum, because more than one is there, generalized momenta definition is completed. How did you complete means? That means I'll say that is equation number 1 and 2. So that is over. So this is your first step. Now the second step is, this is important. The second step is calculation of determinant of the Hessian matrix. So most of the time what happens is without performing the calculation of determinant of Hessian matrix, people proceed further by making an assumption that this is not going to give trouble. Okay, that is an assumption, and straight away without working you jump into the calculation of the Hamiltonian. That is what generally people do. But however, you have to be careful, because when you are writing a competitive examination like the GATE exam or the CSIR NET examination, they may give you a problem where there is some difficulty in evaluation of the Hamiltonian possible, right? So you should therefore know how to calculate the Hessian matrix. What is an advantage or what is the purpose of the Hessian matrix is, Hessian matrix is the one which is going to tell you whether the Hamiltonian is existing or not. That is very important, right? Only if the Hamiltonian exists, you can calculate the Hamiltonian. Suppose if Hamiltonian itself cannot be calculated, then what is the point in trying out? So that is the place where you have to be careful. The determinant of the Hessian matrix, if it is not equal to 0, only then Hamiltonian can be calculated. Otherwise, no. Otherwise, you say that no, Hamiltonian cannot be calculated for the given Lagrangian. Like that, you have to make a conclusion. So for that reason, Hessian matrix is quite important. So therefore, I'll write down now. What is the Hessian matrix actually? So I'll write down that this is Hessian matrix is a square matrix. It is a square matrix. It is basically a second order derivative. You will have to perform two derivatives on the Lagrangian. So I'll write down dou square L. That means you are taking the given Lagrangian and then performing two derivative with respect to what? With respect to the given coordinates. So the general definition is given by this. The general definition is dou, two times you'll have to differentiate. So both of them are dou q dot. You see here, because this is a second derivative here. Here also you should have two derivatives should be there. Now in the two derivatives, the first one will be with respect to the one of the coordinates. The second one will be with respect to another coordinate. Because the meaning is that the standard meaning is like this, where I will take the values 1, 2, 3, etc. up to n, and k also will take the values 1, 2, 3, etc. up to n, where this particular n, whatever n that you are going to write, n is the number of degrees of freedom. So this is how the general expression will look like. It looks something like complicated one initially because of the I and the j, k, etc. But when you are actually writing down the given problem, things will become very clear. Now why it is becoming very clear is that for our problem n equal to 2, that means it is a 2 degrees of freedom system. So what is the meaning is, Hessian matrix, therefore Hessian matrix is 2 by 2 matrix. So this is where the clarity comes now when you are reading theory and problem. Because when you say Hessian matrix, what is the size? Is it 10 by 10 matrix or 5 by 5 matrix? Or what kind of size? So that clarity will come when you work out the problem. So since it is a 2 degrees of freedom problem, Hessian matrix will be a 2 by 2 matrix. In general means I have written here, right? In general here, this is n degrees of freedom, right? Which means that the Hessian matrix will be n by n matrix. So this is the shorthand notation. Remember this particular thing, what I am showing, the white color cursor is now rotating, right? So whatever this expression is the shorthand notation for the n by n matrix. You have to expand with I comma j, then automatically the matrix will come into picture. So now actually we are going to expand for the case of the 2 by 2, and therefore you can really feel where is the matrix coming into picture. So I'll write down, therefore that particular Hessian matrix is given by, so I'll put a bracket here, so you'll feel that a 2 by 2 matrix is coming into picture. And then now we can write down the elements. So what is the first element? Is going to be dou square L divided by, here you'll have to see I and j, whether j, k, I, j, whatever it is, I, j, k, l, m, n, anything can be substituted here for the suffix, okay, where the suffix is going to run from all the way from 1 to the maximum number of degrees of freedom. In our case, I is equal to 1 and I is equal to 2. Only two things are there. Therefore, let me write down for clarity how to write. I will first of all tell you, then the rest of the thing can be done easily. First of all, you write down dou q dot. Because as I already told you, how did I write this one? First of all, I have written dou q dot. Okay. At the end only, I have kept the suffix k and I. In the same way, you can do this, and therefore you'll have to fill out this particular thing. The later we will fill out what is this suffix there. So first of all, fill out this dou q dot, and then make it a 2 by 2 matrix. If it is a 3 degrees of freedom system, you have to write down 3 by 3 matrix. Okay, that is the plan. And let us first of all finish now for our problem of 2 by 2 matrix. So we will be writing like this: dou q dot. And once again, dou square Lagrangian divided by dou q dot. This matrix is known as the Hessian matrix. Now let us fill out I comma j, which will take values from 1 to n. For our problem, 1 and 2 only. Therefore, the matrix will have 1, 1. This is a 1, 1 element. I think that is quite simple, you know. How do you write the matrix? A1, 1, A1, 2, A2, 1, A2, 2. That is the standard way. So you note down what are the numbers here. 1, 1. So what is the number that is corresponding to this? Is 2, 1. This is a 2, 1 element. This is 1, 2 element. This is 2, 2 element. So this is the standard notation for the matrix. So that is what this 1, 1. This 1, 1 is that 1, 1. Okay. So what will be the second one? For the second one, you have 1, 2. So therefore, this must be a 1, 2. This will be a 2, 1. And this will be a 2, 2. So now it is clear that you'll have to perform these 4 partial derivatives. You'll have to evaluate from the given Lagrangian, and you can simplify very easily. You know, afterwards it's only evaluating the second order derivative. So that is quite simple. Before that, let us make it clear that this is dou square L divided by what is 1. You should be careful. So let me once again write down q1 means r. Q2 means theta, and then the corresponding dot you can keep. That means if there is a Q1 dot, I have to put R dot. If there is a Q2 dot, I will have to put theta dot. So do that now. Now that is what you will have to do here. So here let us do this. Q1 dot means what? It is dou R dot. So therefore this is actually dou R dot. I think 2 times it is coming. Therefore we will say that this is dou R dot square, because both of them are identically same. Q1 dot. Then second element is dou square Lagrangian divided by dou q1 dot. So I'll write down dou R dot. Then second one is dou q2 dot. Q2 dot is theta dot. And similarly fill here dou square Lagrangian divided by, this is dou theta dot, dou R dot. And the last element is dou square Lagrangian divided by dou theta dot square, because they're identical. And this is, and once you have this, now you have to let me write down this. Now you'll have to check, now see the, what you have to see the given Lagrangian, and do, that means do the second derivatives. perform the derivatives. So if you perform the derivatives, what are you going to get? So we can check that. So I think we have already obtained some expression for the first derivative. Therefore, you can calculate this. So I'll be getting m here. And here there is no dependence on r theta. Therefore, second derivative is 0. And here also cross derivative, there is no cross derivative term. If you want, you can check out, you simply perform the derivative, take the given Lagrangian. And here, dou square L by dou theta square, you have to be careful. Because theta dot is already present in the system, so you'll have to evaluate. It is there here. It is there here. See, what I'm telling is this one. So you already calculated, right? You have already calculated dou L by dou theta dot. So you perform once again theta dot. Once again, you'll have to perform the theta dot differentiation. So if you do that, we will be getting m into r. So that's what I'm planning to write. So that will give you m into r here. And that's all. So this is the Hessian matrix. So if this is the Hessian matrix, what is the determinant of? Determinant of the Hessian matrix is equal to, determinant means you know, right? You take this multiplication, I'll get m square. And then what about the first one is only m into, the last differentiation I'll have to verify. You check it out whether it is m into r. Yeah, so there is a 2 is there, r square. So that's what r square, right? So the r square. Where is r square? Here it is. This r square only I'm telling. Okay. So that is the one that got missed out. So I'll be writing this r square here. So therefore we will be getting m square r square minus 0. So that is equal to m square r square. And our conclusion is that this is not equal to 0. So now we are making a conclusion that since determinant of the Hessian matrix is not equal to 0, we can calculate the Hamiltonian. So this is the conclusion. So which means that we can proceed further for the determination of the Hamiltonian. That is the meaning. So let us therefore we will continue. So therefore the step is that the transformation, I'll write down the LT. LT means Legendre transformation. The definition for the Legendre transformation is that the Hamiltonian is given by P into Q dot. Let me write down with appropriate summation. So summation Pi Qi dot. Okay, where I takes the values from 1 to n minus the original Lagrangian. So this is the this particular expression is the standard definition, or the way in which we define the Legendre transformation is like this. The summation is important whenever you have more than 1 degrees of freedom. If it is only 1 degree of freedom, summation is not required. Okay, you can simply write down PQ minus L. So PQ minus L is easy to remember. This is for 1 degrees of freedom system. Whenever number of degrees of freedom is increasing, you'll have to add the summation only for the first term. Remember, the summation is there only for this. For the Lagrangian, there is no summation. That is the meaning. Okay, so now let us expand this, which means that we'll have to substitute I equal to 1, I equal to 2. So let us write down that if you are expanding this, I'll be getting P1 Q1 dot plus P2 Q2 dot. So that completes the summation. So that's why I'm putting a bracket. So now the summation is over, minus the given Lagrangian. So now you can understand the meaning of the summation coming here, and n is the number of degrees of freedom. Since we have 2 degrees of freedom, we have only 2 terms coming to the system. So now you'll have to substitute the values for the q1 dots and q2 dots. So let us therefore I'll write down. So I'll write down this, get the values for, okay, get the values for this q1 dot and q2 dot, q1 dot and q2 dot. From where will you get? We have already calculated. I think we'll have to see what is the equation number. Let us go back and verify where it is. It is there here. So it is there from equation number 1 and equation number 2. Okay, so I think this is 1 by 2. 2 is cancelling. Okay, 2 is cancelling. M into r square. So here also 2 is missing. So m into r square, this is the one. So equation 1 and 2. So take from the equation 1 and 2. So get the values for q1 dot and q2 dot from equation 1 and 2. So that gives you, so that gives me the Hamiltonian is equal to, so let me substitute those values. So what is this? P1. P1 is P1. As such, you don't have to do anything. Okay, so here what I have done is only I am just using that q1 should be r, q2 should be theta, and then the original given Lagrangian you simply write down. That's what I have done. And now you can actually substitute those values from equation 1 and 2. So this p theta multiplied by theta dot, you'll have to get it from that equation number 2, which is equal to I think this is p theta divided by mr square. So that is coming from equation number 2. Okay, this is coming from equation number 2. Then minus this expression. Once again we'll have to simplify, and let us keep this as half m into, so what is r dot square? Once again we'll have to use r dot square, pr by m whole square. So pr by m whole square plus r square, and again you have theta dot square. So this is p theta divided by mr square. So that whole square. So half m is again common for these two things. Then minus you have k times r. That closes the bracket. So this is the step which is important. So let me therefore explain that r dot, wherever there is an r dot here, in that place you will have to use pr by m. This is very important step. Okay, so this procedure or this particular step is called the inversion. Okay, you are actually finding the inverse function, and therefore technically this is known as inverse function. Okay, even though it appears to be simple that you take it from the equation number 1 and 2, actually you'll have to repeat this wherever there is an r dot present. You see, you have to carefully see there is an r dot present here, right? So that r dot has to be replaced by this pr divided by m. Where from you got pr divided by m? You got it from equation number 1. This process is called inversion process, okay, or we say inverse function. Similarly, theta dot, wherever there is a theta dot coming, you'll have to replace by p theta divided by mr square. So that is there here. This is your p theta by mr square. Here also same thing is there, which is coming from equation number 2. So this procedure, whatever I am showing the arrow, that is called the inverting procedure, or it is the step, inverting step actually. This is very important. If you don't do the inversion, then the final Hamiltonian is incomplete, or you are not calculated correctly. So that is why I am emphasizing this point. Inversion step is very important. All the dotted variables with r dot and theta dot, they have to be eliminated. That's very important. So if you want, I'll write down. So the above step is elimination of, that means removal of. Okay, elimination means removal of. Okay, elimination of all the dotted quantities. Okay, this is known as inverting. This is known as the inverting step. So I just want to give you the emphasis on the technical term or the terminology used, okay, rather than taking the problem and solving. The inverting step is something that you'll have to be careful. Let me therefore define some basic thing, then we will come back to this. The inverting step is something important. So here I will explain. I will write down here the inverse function. I will write down this. The inverse function of sine theta is given by sine inverse of theta. The second one I'll write down the inverse of the function sine theta is given by 1 divided by sine theta. So did you get this point? These two are not same. You have to be very careful. This is inverse function. Inverse function is different. Inverse of the function is different. So there is an off coming here. Here there is no off. This is known as inverse function. The second one is known as inverse of the function. You know that sine inverse of theta and 1 divided by sine theta, they are not the same. They are not same, right? So that is where the important point you'll have to be careful. In the case of our Legendre transformation, we are doing this step. That is why I am telling it's very important. You are actually doing the inverse function calculation from equation number 1 and 2. Okay, it is not the inverting the function. So this little bit of technical point should be clear to you. And therefore, whatever we are doing right now here, what is known as the inverting step, it is not 1 by of that. Okay, we are not writing 1 divided by of that quantity. That is only inverting of the function. That is inverting of. We are not doing that. It is the inverse function we are doing. So this particular step is very important, and it is coming from equation number 1 and 2. So that is the meaning. You see this one. From here you have to get. Okay. From here, what will you get? You just see this from here. What can you write down from theta dot? So theta dot can be written down as p theta by, that is what I am writing, p theta by mr square. So when you are going to use this particular substitution, where are you going to substitute this is, you will have to substitute this expression in the original Lagrangian. So where is the original Lagrangian? It is there here. So you will have to substitute in this place. Okay, if you are doing that, then you are finding the inverse function. So that is what it means to say. So when you are performing the inverse function, then it is actually doing the Legendre transformation. So in the Legendre transformation, that is what is happening in the geometrically. Okay, so that is why this particular point or the concept should be clear. And once it is clear, then the rest of the thing is only a matter of simplifying this expression. So now it is only a matter of simplifying. You can find similar terms here and then add and subtract. Okay, there are similar terms are there. So where are the similar terms? Let me tell you. This is PR square, right? So here also PR square. So that particular step is there. Here you have divided by m, and here you have 1m is there. So if you subtract them, I will be getting. So I'll simplify this. Then PR square divided by, here 1m is there and here 2m is there. So after subtracting, we will get 2m. Then you get a plus. And here you have p theta square. So here also you have p theta square. So I'll write down that this is p theta square. Okay. And divided by, here you have mr square. Here what happens is that there is a m square r to the power 4. Isn't it? So there is an m square. Then you have an r to the power 4. But there is an r square here. So I'll write down numerator r square is there. And what else is there? There is a m here in the numerator. And then 1 by 2 is there. So these are the things available. So let us cancel. So if you cancel, what is happening? 1 by 2 is there. Then you have mr square is there. So therefore, you will be getting mr square. This is 2. So again, you will be getting 2 times m times r square. So all the things are now coming clearly. Then this is over, this is over. Then final expression. Final expression is this last one. So I'll write down plus, because minus of minus, k times r. So this is k times r. And that's all. And once you finish this expression, we say that this is the Hamiltonian. And before putting this box, okay, you'll have to verify whether this is acceptable expression or not. Okay, how do you know whether it is an acceptable expression or not? How do you know that is that you'll have to check. What is that you'll have to check is that the Hamiltonian should be a function of, I'll write down this, Hamiltonian should be a function of q comma p comma t. So that this is the standard rule, right? Q comma p comma t. So anyway, for now we don't have time, so let us forget about that. Do you have q comma p? That is the question that we have. So we'll have to expand and write. How many q's you have? 2 q's you have. So I have q1, q2. How many p's we have? 2 of them. So I'll write down p1, p2. We don't have time. So therefore, we will be writing like this. What is q1? Q1 is r. q2 is theta. So p1 is pr. p2 is p theta. So what is that you are going to check is that whatever equation that you obtained here should be a function of r theta, pr, p theta, and nothing else. That is what I mean to say. And it should not contain, this is very important, this should not contain any dotted variable. So that is very important. It should not contain any dotted variable. What do you mean by that? What do you mean by dotted variable? Means it looks like r dot, theta dot, etc. So such kind of r dot, theta dot should not be present in the Hamiltonian. That is very important. So now you check it out here. We have pr square by 2m. So there is a pr. So I'll put a tick. PR is there. I will come here. M2 and m is constant. Forget. P theta is there. So yes, there is a p theta. So put a tick here. K constant. Then you have r here. So r is here. Theta, okay, theta is allowed, but theta is not present. That is fine. So if certain variable is missing, then we say that it's a cyclic coordinate, and then we can always say that the corresponding conjugate quantity is a conserved quantity. So those things are a different thing. But right now, you agree that the dotted quantities are completely eliminated. You see that the expression for the Hamiltonian should not contain dotted variable. This is very important. If you have some dotted variable with you, then that is not acceptable. The expression for the Hamiltonian, it will be rejected. So the methodology for finding the Hamiltonian should be now clear. It involves the defining equation for the generalized momentum, followed by the calculation of the Hessian matrix, and then check whether the Hessian matrix determinant is not equal to 0. Okay, you know what do you mean by that? It means that we are actually calculating the some kind of inverse, singular matrix, right? Singular matrix. Why do you worry about the singular matrix when you want to invert the matrix? A inverse. Okay, A inverse. You remember A inverse, when you calculate, you'll be worrying about the singularity of the matrix. And now you see, this is like finding the A inverse of a matrix. If A is a matrix, then A inverse. When you are finding the inverse, singular matrix should not come into picture, and that is why the Hessian matrix is coming into picture, and it is giving you a guarantee that this is the place, and the Hessian matrix will give you a guarantee that you can proceed further for finding the inverse function. It will be successful. So certain things like this, technical points are going behind. So it is not only the simplification of some steps. Okay, the concept should be clear. Once it is clear, then any given Lagrangian you can work it out. This problem is very important because every time you can find out, every year you will find out GATE examination or the CSIR NET examination. There will be one question on converting the Lagrangian to the Hamiltonian. Okay, most of the time you can make a mistake, or sometimes you can you do not know whether the Hamiltonian exists or not. Okay, so the existence comes from the Hessian matrix. So this is the point that is clear now, and I think we will come back to this particular second question in the next lecture. I mean, I'm talking about this one, how the Hamiltonian is total energy. Now the answer can be done very easily. So that we will see this one we will see in the next class. Okay.